And we are back, and we are going to continue our discussion about probabilities and continue into a section of conditional probabilities. So here we are going to calculate probabilities based on an event effectively occurring. So for example, we are going to calculate the probability that A will happen given that B has occurred. So the conditional probability of A given that B has happened. So let's go ahead and do this with an example. So what is the conditional probability that we pull an ace given that it's also red? So we're a little bit fortunate, and we can cheat a little bit in that we've actually already calculated this, that the probability of, basically pulling an A, these basically non-mutually exclusive, not mutually exclusive events here. So we can actually work and continue with this. So we could actually plug and chug this into our system. So remember that previously that was our intersection probability of A and B occurring. So remember that this symbol here is basically an intersection, so probability of A and B occurring. And that is distinct from here, which is our, this is our union symbol, and it's basically the probability of A or B occurring, so A and B. So we actually have this, and we calculated it previously, and we know the probability of B, the event that a card is red, is 1/2, so we could actually calculate that out, and you get this, and that's equal to 1/13. You could also logic this out. So basically, what is the probability, again, of A, basically that our card is an ace, given that we've pulled a red card? So if we pulled a red card, we know that there's 26 red cards, and 2 of them are aces. So we can kind of logic out as well that it should be 1/13, which is the same here. So you can use this general section, what is the probability of A and B happening over probability of B, and vice versa, and we can kind of logic that out. You can also rearrange this this conditional probability as well. So we could put this on this side here, and you can do the same thing for A and B, or B and A, vice versa. Again, as long as we assume that the probabilities are non-zero for both A event and B event, then we can logically make the conclusion that for the probability that A and B occur, A and B will be independent events if and only if that is true. So this relationship must hold. So let's see if we were correct on that. So in this problem, we said, again, RA, let's go back. RA is that we pulled an ace. So we can see if they are independent. And our B was that it was red. So we know that the probability of B, yes, we know that probability of B, let's go up here, make sure that we don't have, or actually we can flip these, or again, A and B, doesn't matter. So for this example, let's say that A and B, actually what we had previously, because in the previous example, we said that A was red and an ace. Yes, A was red and that it was an ace. So we can confirm this as well. So probability that it's red is 1/2. Probability that it was an ace is 1/13. We could find that this was equal to 1/26. And we see that we have an equality, and therefore they must be independent events. So we can confirm that essentially and prove that this is a truly independent. So A and B. So we've got it here. So we can kind of see, maybe that may change if you don't replace, but we'll come to that in the next session. So see you in the next video.